Now we're going to go a little bit beyond what we did before with power series representations of functions. The real reason power series are nice for representing functions is that everything we do in calculus works very well with power series. Power series are essentially like big polynomials, like an infinite degree polynomial, but we really shouldn't say that exactly. We call them power series. But we can think of them as very much polynomial-like because when it comes to both differentiation and integration, you can do those things term by term, and each term is, of course, a monomial. That's what makes it very much like a big polynomial. The formal statement of this comes from the book here. If we have a power series, here I've represented a power series centered at A, and it has a radius of convergence R, which is a positive number. We're never interested in power series really when the radius of convergence is 0, and if the radius of convergence is infinite, that's great. That will certainly count here as R being greater than 0. So at least as long as R is finite, that means that the interval of convergence is an interval centered at A of radius R. The series might or might not converge at the endpoints of this interval. We'll deal with those things later, but at least it converges on the open interval of radius R centered at A. So if you have a power series defined by f of x is c0 plus c1 x minus a plus c2 x minus a quantity squared, etc., we can write that in standard notation, sum of c sub n times the quantity x minus a to the n. That power series will be differentiable, certainly continuous, on this interval from a minus r to a plus r, or if r equals infinity, the entire real line, if the radius of convergence is infinite. And furthermore, the derivative of that function will be what you get when you differentiate term by term. When you differentiate c0, that becomes 0. When you differentiate with respect to x, c1 times x minus a, you get the c1. When you differentiate c2 x minus a squared, you get 2c2 times the quantity x minus a. And you keep going like that term by term. That's very easy to write in summation notation because you just take these terms and differentiate each one. When you differentiate c sub n times x minus a to the nth power, you just bring down the n, you get n times c sub n times x minus a, that I wrote that incorrectly, so let's fix it here, to the n minus first power. Now, it's okay to keep going from n equals 0 to infinity, but the n equals 0 term just gives you a 0 here in this formula, so we've written it sum from n equals 1 to infinity. But if you put n equals 0 here, that's okay. You would just get an extra 0 involved there. Now, it's not just true that we can differentiate a function with a power series representation by differentiating term by term. We can integrate a function. If we want the indefinite integral of f of x dx, that will of course be some arbitrary constant c. We're just writing it at the beginning for convenience, plus what you get when you integrate each term one by one. The integral of c1, I'm sorry, go back to here. We integrate each term. The integral of c0 can be c0 times x minus a. We're writing it x minus a here because we're integrating to get a power series centered at a. Integral of c1 will be c1 times the quantity x minus a squared over 2. Integral of this will be c2 x minus a cubed over 3, etc. In other words, when we integrate this term by term, we just get c sub n times the integral of this x minus a to the nth, which is x minus a to the n plus first power over n plus 1. And don't forget our arbitrary constant c from the beginning there. So power series representations give us a way to represent a function as a power series, which we can think of like a big polynomial, and it can be differentiated or integrated term by term, just the way you would do for a polynomial. The really important kicker at the end is if you started with a power series which has radius of convergence r, then whether you differentiate or integrate the function f, the radius of convergence doesn't change. The radius convergence stays r. In other words, these will converge. These things, meaning the power series for the integral of f and the power series for the derivative of f, they will still converge on this interval from a minus r to a plus r. Remember, it will be the whole real line if r equals infinity. Here's something that's a little bit strange. Remember, some power series can have an interval of convergence that includes one or both of the endpoints. And strange things can happen with the endpoints. If your original function has a power series which converges at one of the endpoints or both of the endpoints, then the derivative and the integral might or might not converge at those endpoints. We're guaranteed by this theorem that everything will converge on this open interval. What happens to the endpoints can change when you differentiate or integrate your power series. In fact, things could be nicer. You might have a function f which only converges on the open interval. When you integrate it, you might end up with a function that converges at one or both of the endpoints. So we're going to have to be careful with what happens at the endpoints, but at least on that open interval, everything's guaranteed to be nice. Let's see some examples of this. Let's start again with 1 over 1 minus x. This is kind of the simplest, most basic power series representation of a function one can have, because the series here is a geometric series, which we know is equal to 1 over 1 minus x. Remember, this is valid when the absolute value of x is less than 1. In other words, r equals 1. The radius of convergence is 1, and this is a power series centered at 0. What's the derivative of this function? Well, just by calculus, we know the derivative of 1 over 1 minus x is, by the chain rule, minus 1 over this quantity squared times the derivative, which is another minus 1, and the two minus 1's cancel, so we get exactly 1 over x minus 1 quantity squared. What's the power series for 1 over the quantity x minus 1 squared? Well, it's exactly what you get when you differentiate term by term. When you differentiate the 1, you get 0. So I won't write that. When you differentiate the x, you get 1. When you differentiate the x squared, you get 2x. Then you get 3x squared, 4x cubed, 5x to the fourth. This will be equal to, I should have mentioned this, of course, is we already have that here. This will be equal to a sum from n equals 0 to infinity of n times x to the n minus 1. And notice I wrote n equals 0 to infinity. The 0 term, the n equals 0 term is 0, so I could have written this as n equals 1 to infinity. It would make no difference. What's the radius of convergence here? Again, the radius of convergence is still 1. In other words, it's still valid when the absolute value of x is less than 1. If we just check the endpoints separately, you can see that when x is equal to 1, you get the series 1 plus 2 plus 3, etc., which very clearly diverges. The partial sums blow up. And if x is minus 1, again, you get a divergent series, because, again, the individual terms won't be tending to 0. Things kind of blow up, though they do alternate in sign. So really, this series is valid on this exact same interval, the interval minus 1 to 1. Let's differentiate one more time. What's the second derivative of 1 over 1 minus x? Well, if you differentiate this just using calculus, you get minus 2 over x minus 1 quantity cubed. Make sure you're comfortable differentiating that. And we get, if we differentiate this term by term, we get the 1 goes away when we differentiate it to 0. The 2x gives us a 2. Then we'll get 6x, we'll get 12x squared, we'll get 20x cubed, etc. We can write this as a sum of n times n minus 1, x to the n minus 2. Notice here we could start at 0, but then this quantity would be 0 when n is 0 and when n equals 1. So we get the exact same thing if we just start when n equals 2 as we would get if we started when n equals 0. That should be a 2 there. And again, it's valid with the same radius of convergence. In other words, valid on the same open interval, the same interval minus 1 to 1. Let's look at some more examples. Again, I've rewritten this formula for a basic power series, which you should come to understand really well. 1 over 1 minus x is given by this power series, again, when the absolute value of x is less than 1. So let's look at log of 1 minus x plus c. That's the integral of 1 over 1 minus x dx. Actually, I wrote that incorrectly. Minus log of 1 minus x plus c is equal to this integral. Got to get your signs right here. This is equal to now the integral here, term by term. When I integrate each term by term, I get x, that's the integral for 1, plus x squared over 2, plus x cubed over 3, plus x to the 4th over 4, that's integrating the x cubed, plus x to the 5th over 5, plus x to the 6th over 6th, and we keep going. That's going to be a sum. We could write n equals 0 to infinity, and then just integrating term by term, we get x to the n plus 1 over n plus 1. Shifting index, you could see that's the same as starting from n equals 1 to infinity of x to the n over n. It's fine to leave it like this. Now my claim is, first of all, it's valid with the same, for these same, with the same radius of convergence, r equals 1. In other words, on the same interval from -1 to 1. Let me just take this and solve for log of 1 minus x. I can put the c on the other side, and I'm not even going to worry about changing its sign here. C is an arbitrary constant. I have to multiply by -1 for the log x, so I get log of 1 minus x is some arbitrary constant c minus x plus, and it's not an arbitrary constant here, we'll talk about that in a second. Log of 1 minus x is c for some constant c, minus x plus x squared over 2 plus, I'm sorry, these should all be minus because of that minus sign, minus x squared over 2, minus x cubed over 3, minus x to the 4th over 4, etc. All coefficients have the minus signs. And then we can actually find what c has to be to get exactly this function log of 1 minus x. When x is 1, the left side is 0. I'm sorry, when x is 0, this is 0. It's just log of 1. So when x is 0 over here, we need 0. That tells us c equals 0. So let me write this again. We know when c equals 0, this has log of 1 minus x has to be exactly minus x squared over 2, minus x cubed over 3, etc., which is just a sum from n equals 0 to infinity of minus x to the n plus 1 over n plus 1. Now, I'm going to talk about this one just a little bit more. Notice this is still valid on this open interval from -1 to 1. In other words, the radius is 1, as we said before. But what happens if we were to plug in x equals -1? On the left side, we would get log 2. On the right side, when we plug in x equals -1, let's put it in here, this becomes 1. This becomes, when I plug in x equals -1, we have -1/2. When I plug in x equals -1, the minus cancels with the -1, and we get plus 1/3, then -1/4, plus 1/5, etc. And this converges. So it turns out this series for log of 1 minus x is guaranteed to converge on this open interval from -1 to 1, but it converges at -1 as well. And I claim, though I won't prove it here for you, that by a continuity argument, the value when x equals -1 is exactly the same as what you get by plugging in -1 here, in other words, log 2. That's how we know that log 2 is the value of this alternating harmonic series. Check. I want all of you to check yourselves that when x equals 1, the series diverges. You just get the -1 times the harmonic series there, which diverges. So the interval of convergence is actually the half-open interval from -1 to 1. Often we won't be interested what happens at the endpoints. Here it's pretty interesting what happens at this left endpoint because it gives us a beautiful value for the alternating harmonic series. But the general theory says it's guaranteed to be nice on that open interval whose radius of convergence, in this case, is just 1. We're going to look at one more example. And we'll start with this series for 1 over 1 plus x squared, which we derived in the last video. That's just 1 minus x squared plus x to the 4th minus x to the 6th, etc. It's just exactly what you get from this series up top here when you substitute in minus x squared for x. And we know it's valid when the absolute value of x is less than 1. In other words, the radius of convergence is 1. Arctangent x is just an antiderivative of 1 over 1 plus x squared. In other words, the derivative of arctangent x is 1 over 1 plus x squared. So to get arctangent of x, we integrate term by term. And we always have to be careful when we do that. There's some constant c that can come in. And then we have x is the integral of 1 minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7 plus x to the 9th over 9, etc. If we want the general formula, we'll talk about the general formula in a minute. This is a series representation for the arctangent of x. But what is c? Remember, we just derived this by knowing that arctangent of x is an antiderivative of 1 over 1 plus x squared. Again, if we plug in 0 on both sides, we get 0 on the left, and all of these things are 0. So we get c must be 0. In other words, the arctangent of x really is exactly x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7 plus x to the 9th over 9 minus etc. And now we'll write this series representation in summation form that looks just like what we get when we integrate this term by term. So we have the minus 1 to the n, integrating x to the 2n term by term, we get x to the 2n plus 1 over 2n plus 1. You can plug in a few terms. Here's what you get when n equals 0, when n equals 1, when n equals 2, etc. Now, for which x is this valid? Again, it's valid when the absolute value of x is less than 1, that's for sure. Here's something really neat. If we plug in x equals 1, this series on the right, 1 minus 1/3 plus 1/5 minus 1/7 plus 1/9, is an alternating series whose terms are decreasing and have limit 0. So this actually converges. So the actual interval of convergence is going to be minus 1 to 1, now including 1. If you plug in x equals -1, you can actually see that the series will converge then as well. So I should actually put that in there too. It's good at -1. But plugging in x equals 1, we get arctangent of 1 is equal to that series. Well, arctangent of 1 is just pi over 4. So here's a beautiful series representation, not a function, but just a numerical series representation for pi over 4. It's 1 minus 1/3 plus 1/5 minus 1/7, etc. In other words, if you multiply both sides by 4, you get a nice series representation for one of the most important numbers in mathematics. Pi is just going to be 4 minus 4/3 plus 4/5 minus 4/7, etc. Now, there are many, many, many different series representations that people have found for pi. Some of them converge much, 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 much more quickly than this, and are actually the things people use when they're doing numerical approximations for pi to large numbers of decimal places. People know pi to literally billions and billions of decimal places right now, using series representations. Not this one, because this series, even though it does converge, converges pretty slowly, but they use other much more complicated series representations for the number pi.